At the beginning of a talk, you are supposed to give a few thanks to the organizer who invited you, and I realized that this is the first time the organizer is one of my ex-students, so I began to feel a bit of nostalgia and like an old-timer, but still thank you, Malek. So I have also the task to introduce a completely different subject, which is non-commutative field theory, and also renormalization, because so this...
Switch it on, probably.
Turn the microphone on.
Sorry?
Turn it on.
What's the problem?
Lumière rouge, allumée. Faut l'allumer.
Yes, okay. Is this on? Thanks.
Let it get back to the beginning.
So there will be... Is it okay?
Yeah. It was the same for us.
All right. That's
For academic.
So there will be some... I'll try to give us... to give a little bit of combinatoric flavor to this talk. But essentially, there will be some physics in this talk about field theory, because that was the main reason I get really interested into the non-commutative field theory. But now we have found so many interesting combinatoric aspects that I hope you will enjoy some of the objects that we'll see here. So we have seen trees and forests and so on. And trees and forests appear in almost endless variations in field theory and renormalization theory. You have perhaps heard about the topological polynomials in Feynman amplitude, about words such as Zimmermann's forest, Galavotti-Niccolo trees, Kohn-Kreimer Hopf algebra, which is based on trees. And we had a lot of recently of cluster expansion, Meyer expansion, and forest formula, and they are the daily bread of constructive field theory, which I will tell you in a minute what is about. So this is not surprising, because at the core of field theory or renormalization lies the problem of computing connected quantities, and the simplest way to connect things is through a tree. So non-commutative field theory leads to a new variation of this theme. And there are new objects, and my talk is also a bit of an introduction to three other talks. Razvan Gouraud, which will talk about new non-commutative polynomials, Adrien Tanassa about new Hopf algebras, and Jacques Magnin about new cluster expansions. So I had not a privilege to know Pierre Leroux, so I was moved by what I heard about him, and therefore I'll try at least one sentence with a little bit of his language, saying that probably he would think of a quantum field theory as a kind of a generating function, but for a certain particular species of graph, and then it has some weights. And we are very much interested in the weights, which is usually what the combinatorics perhaps are not interested in.
We have the weight.
Yes.
Okay, yes. So in field theory, usually the weight associated to a graph is called amplitude. So that's also a question of vocabulary. And you have to distinguish two different problems. One is that some of these weights can be defined by integrals, for instance, which are formally divergent. And the series itself might have a zero radius of convergence.
What is the radius of convergence?
Okay.
Of series 1 plus infinity plus infinity?
Yes. So wait and you will see. So renormalization theory addresses the first problem, and when the first problem is addressed, really you can try to look at the second one, which is addressed by constructive field theory. Okay, Alan?
Yeah.
Fine. So yes, it tries to distract me. Okay, renormalization physically is much more general. It originated in the problem of removing infinities in field theory, but it's much more general than that. In fact, in physics, it is a very general framework which tells you how a physical model or a system will change, his appearance will change when you look at it at a different observation scale. Mathematically, you could say it has to do with some kind of iteration of a certain renormalization group map, which involves only convergent weights because it is a problem concentrated on a single scale, roughly speaking. So I suppose in combinatorics terms, it has to do with some kind of iteration, infinite iteration of a certain composition map on species, if you like. And constructive theory, I would say, I would like to distinguish about, if you like, for a single step of this iteration, it looks at the problem of G itself, and now the G, the weights are finite, as you wanted, Alan, and then we can ask whether we are inside a radius of convergence, and typically one is not, but if some parameters is small enough, we could be inside a Borel radius of convergence. That is, the initial series could have, for instance, Borel sum, and then that could be proved for small coupling. As a problem in terms of species somehow is to pick up into a big species of graph a smaller pieces of trees, because that will help getting better estimates. And then multiscale constructive theory tries to combine the two previous steps in a consistent way. But there is a snag. And the snag is that usually, after the first two problems have been correctly tackled, the flow of the composition map, which is delivered by the renormalization group, wanders out of the radius delivered by constructive theory, so you cannot iterate it consistently to infinity. And unfortunately, this phenomenon always occurs in ordinary four-dimensional field theory, either at what we call the ultraviolet or the infrared end of the renormalization group. I'm going to tell you a bit more about this language. But this is a generic feature of four-dimensional field theory, and except possibly for extremely special models. And this is very frustrating.
Could I ask a quick question?
Yes.
It could just be names. When I see Borel, I think of regularization rather than renormalization. Do you
Okay.
mean the same thing there, or?
Well, I use the word Borel only in connection with the question of when you have a theory, a power series which is divergent, it might nevertheless be at the border of an analyticity zone, and then you might have a unique way of associating a function to the information contained in the coefficient. That's what I wanted. Of course, Borel made a lot of different theorems, but that's the one I had in mind.
Regularization has a different meaning also.
Yes. So it's not. It has nothing to do with Borelian sets and so on. I was just saying we typically have divergent series, but nevertheless the information is contained in the coefficient if we can, for instance, can prove that the series is Borel summable, which means usually constructing the function through other means and then a posteriori checking that it is Borel summable. Okay. So this snag is frustrating. And I am going now to try to explain this in a bit more detail, and I will be helped by the previous talk of Abdeselam, so I can go relatively fast. So he told you how the 5-4 model in field theory is formally an interacting measure of this kind, in which lambda is called the coupling constant. M is the mass which fixes some scale in the problem, after which you will stop the iteration of the renormalization group, so you will have only half a direction which goes to infinity in this renormalization group. A is called the wave function constant. It is usually fixed to 1, but I will need a bit of discussion later about it. Z is a normalization, so this measure should be a probability measure, and d phi is this formal ill-defined product of Lebesgue measures at each point. So there is obviously a lack of some analysis there. The function cannot be completely independent of the value of the neighboring points, otherwise you don't have anything reasonable anymore. So to get rid of this first problem, you just group everything which was quadratic together, and you define this Gaussian part of the measure, which also Malek introduced. So you realize that it corresponds to Gaussian measure with a covariance, which in physics is called a propagator or free propagator, which is just a discrete function of 1 over p squared plus n squared. And a good way to analyze it is to write 1 over an operator as when it is positive as the integral from 0 to infinity of exponential minus t the operator, or minus alpha the operator. And we recognize that in the case of 1 over p squared plus m squared, this would involve the heat kernel. So C of xy is the integral over the heat kernel. Then you get Feynman rules. So again, Malek explained a bit this. You have now the interaction measure, which is given by the prefactor exponential minus 5,4 times d mu. we are still far from well-definedness because the support of T mu is distributional and a product of distribution is ill-defined and so on. But for the moment, just forget about all of this and look at the Schwinger functions. They would be the moments the moments of this measure. You see? So they might have n position, capital N position, which I call external. All right. So expanding into this exponential as a formal power series, we would get here Gaussian integrals of polynomials in phi. And then we can use the formula that David explained us, the Wick theorem, applied to this series terminates, and therefore we get a finite sum of objects, which are the Feynman graphs. So how many do we get? Well, if we have 4 little n plus capital N fields, you know the 4 little n came from here and the capital N from here, then the number is a double factorial. You know, it's very simple. It's a number of pairings them together, and the physicists draw these drawings called Feynman graphs or contraction schemes. For instance, here I had four external points in my Schwinger function and 3 internal vertices, and this is one of the many contractions that I could write.
Your internal vertices should be x1, x2, x3, I guess?
Yes, there is a misprint, x1, x2, x3, right, you're correct. It's very important not to give the same name to different dummy variables of integrations, otherwise you are lost.
May I ask?
Yes.
So this degree 4 in the vertices, it corresponds to the exponent?
Yes, this is because we tried to construct a theory which has a monomial of order 4 at the same point. So this is exactly that. You should draw the half lines for the physicists are like the fields, and the lines come from contraction from this theorem on 2 fields. And then in a vertex, because you have 4 fields at the same point, you will draw a picture with a single point and 4 half fields. Then what is the Feynman amplitude or weight of the contraction scheme? Well, it's just the integral of the position of the vertices, because that's what you had here. You see, every vertex had to be integrated with its own independent integration variables. And you have the product, the integrand is the product of the lines of the propagator between the 2 points xl and yl at the end of the line. They could be internal or external variables, so that this thing is really a function, in fact, a distribution of the external position z1 up to zn. And you have a combinatoric factor in front. You have to count how many Wick schemes lead to that graph, if you like, in order not to compute the same integrals too many times. And this integral may diverge, for instance, both because some of the integrations may diverge because at large volume on R4, or because you have the singularity of the well-known singularity of the heat propagator kernel at coinciding points. So this singularity is in the language of field theorists or physicists is called infrared. This one is called ultraviolet, because infrared means long distance in physics and ultraviolet means short distances. So I have to talk about the parametric representation. So there is a compact way. Okay, you notice that in the heat equation, the position dependence is quadratic. Then you have a Gaussian. You can integrate it. The result is a determinant. That's the basic observation that led to this compact form. You can integrate over positions because you can integrate explicitly because the object is a quadratic form. And we will see that this is a nice feature which is still true in non-commutative field theory. So you get a formula called the parametric representation, which is like that. So omitting some trivial factors, the amplitude, the Fourier transform in fact of the amplitude. It's easier to express it like that, but you can also express it in direct space. You can factor out an overall delta function of conservation of momenta, and you get an integral which is solely over an alpha parameter for each of the lines of the graph. Okay? And then there is this bizarre integrand, which is made of 2 polynomials, UG and VG, which are called the first and second topological or Simonsic or Birkhoff-Simonsic polynomials. what is interesting remark is that space-time has essentially disappeared, except for the dimension d, which is now a parameter. So what I said before was true for dimension 4, but here I was a little bit more general, and I put d as a parameter. You see that d is a parameter solely there. I'm sorry, this laser pointer is not working, but so it's there, okay? And you could believe it is somewhere also in the external momenta there, but really it will depend only on Euclidean invariants, which are scalars. So in fact, in some sense, it has disappeared also from the external arguments. So what are these Birkhoff-Simonzik polynomials? Well, UG is the sum of the trees embedded in G, that is subset of lines that form a tree, a spanning tree, the product of the line not in the tree, of alpha L, and VG is the same thing, but over the two trees. That is, two trees cuts the graph into two connected components. So this is a graph, for instance. This is a tree, and this is a two-tree. And E of when you have a two-tree,
So I'm sorry, you are cutting off the piece of the graph that is somehow outside.
yes, I've amputated the trivial factors which go to the external arguments.
You only have two external lines?
No, in this one, because the species I look at will have degree 4 at the vertices, I would typically have two external points there and one there. But because I omitted trivial external propagators, I didn't show them in the drawing. Okay, so because you have to have degree 4 there, and also there, let's say, you had to have 4 other lines, which okay?
So you show only the
I show only the internal, yes, on this drawing I showed only the internal lines.
But at each internal.
But you can canonically complete because you know the degrees. So
But at each internal vertex, there's a certain momentum pi being injected.
yes, and that's a spanning tree. And the problem is here you cut it into two, and this invariant is the sum of the pi which arrive there, but it is also the sum of the pi which arrive there because of a delta function in front of AG. So that's the story of the second polynomial.
So,
Yes.
yeah, so this 2, 3, it is a subgraph also. Is
Yes,
a
also,
subset of
yes. So, you know, here you have 1, 2, 3, 4, 5. You have to count about 5 trees, I don't know. And then you take all these trees, and by omitting a line, you get the 2 tree. So I suppose here you have only, let's see, you have...
Two-tree spanning forest consisting of two
Yeah,
trees.
this is a spanning forest, if you like, with 2 connected components. That's what I call a 2-tree. So, all right.
At one point, are there any conditions on the 2 trees other than they are each a tree with an edge removed?
No. There is no condition except that if you by chance divide the graph into connected components and no external momenta arrive on that connected component, you can add it, but the factor here will be 0, so you are working for nothing, but the formula remains true. So there is no condition. So the question is, how do you prove this theorem? So, okay, the proof somehow relies on Birkhoff 3 matrix theorem, which tells you that when you have a matrix which has all the sum of the coefficients, for instance, for each line equals to 0, then if you look at a minor crossing, for instance, of course, the determinant of A is 0, but if you look at a minor by crossing one line and one column, then it will be the sum of the trees on the index set 1 up to n, of the product for the lines of the tree of the directed element corresponding, the directed matrix element corresponding to this line, because the trees here are oriented. So the sum is of the oriented rooted trees with root at point 1 and oriented away from 1. Sorry? Kirchhoff. Sorry. There's
Also maybe
Well, it
Maxwell.
could be Birkhoff, maybe.
Birkhoff? Could be Birkhoff. It's Kirchhoff. I'm
Also
sorry.
before it was Kirkhoff.
It was, so there are several misprints here. So it's, and the thing is a Kirchhoff-Simonzik polynomial, not the Birkhoff-Simonzik. But okay, I am a physicist, so.
This is physics.
Oh, okay, another one. Sorry.
One important point Your matrix A does not need to be symmetric, is that right?
No, the matrix A does not
So
need.
this is
Actually, when
some later
yes,
generalization.
if you use
of
the X space, the direct space position representation of the amplitude, you will find a symmetric matrix. But this is by chance. This is more general, okay? And
you will need the non-symmetric case.
yes, well, no, not necessarily for the parametric. Now, the question is, this parametric representation, there are many ways to compute it. And one is through this theorem with Grassmann variables. But another one is there is another proof which starts directly from X and P, a mixed X and P space representation. And this one is even more interesting because it implies a Pfaffian version of that theorem. And that is the version which will prepare the ground for the non-commutative generalization of this. So you will hear about that and Grassmannian proofs of this theorem in Razvan Gouro's lecture. And I have been told that the next speaker also will introduce Grassmann variables and Grassmann integration. So you will hear more about it. So I will not talk about these Grassmann proofs of these things. Okay, and there are also, well, there are, lots of Birkhoffs to change into Kirchhoff. So I now will go more into physics and tell you about recipes for renormalization, like when you have a good cake to prepare, what are the elements that you need to put in, okay? So there are several elements, at least there are three main ingredients. Okay, I would say there is a scale decomposition, a locality principle, and the power counting. But the first two elements are quite universal. They're like the flour, you know, and the butter and the eggs. But then after that, in each cake, you can put a different fruit, and that gives a different flavor to the cake. So it's essentially the third element, which depends on the details of the model. So scale decomposition is to find this iteration map, namely decompose the problem into a composition map for a sequence of simpler problems. And when available, the most convenient way to do this is to use the parametric representation of the propagator itself, or of, if you like, the covariance. And that can be done like that. You take this alpha representation with the heat kernel. You take your favorite number m, a fixed integer, for instance 2, and then you will say that what you call the problem at scale 2 to the minus I in distances, or 2 to the plus I in momenta, is to integrate only between m minus 2i and m minus 2i plus 1, this thing. Okay, there is a little correction for I equals 0, but you can imagine what it is. You have then to go from 1 to infinity.
And I runs over all integers. Right?
Yes, and I will be overall positive integer.
Why positive?
Sorry, because I have only half of the renormalization group because I put a mass. If you want to look at an infrared or critical problem, you would have to take eventually I over Z. But for the moment, I had put a mass here. This term, you know, I will take a finite non-zero mass, and therefore I will not look at a critical theory in terms of statistical mechanics. I am only interested in the ultraviolet problem, namely large momenta compared to this mass, or small distances.
So
Therefore,
in principle, the integral round from alpha equals 0 to infinity.
yes, and
but you just throw
yes.
in the weight.
Well, I didn't. This formula is true for I bigger or equal to 1, and for I equals 0, there is a different formula. It goes from 1 to infinity. I didn't tell you what is the, and I can make in a single bold step all the infrared scales because I have a mass. So that's a way of looking only at a half renormalization group, if you like. But this is the problem of the ultraviolet limit, which I am going to be interested in this talk. Okay, so then this is not exactly a computation, but an estimate, you see, because of this, roughly speaking, this gives you the propagator of this, the behavior of this. That is, if x minus y becomes much larger than m to the minus I, which is very tiny, then this slice propagator will essentially be 0. So you could say that higher and higher values of the scale index I probe the theory at shorter and shorter distances. So that's the scale decomposition. Then, because you have decomposed the propagator, it means that you have a price to pay for any graph, you have to sum now over such an independent scale index for each line of the graph. And I call this attribution. And then at fixed scale attribution, there are some subgraphs which play an essential role. They are the connected subgraphs for which all internal lines, they all have higher scale index than all the external lines of the subgraph. Okay, so you have to digest this sentence. I put it in red. And then I'll call these graphs the high subgraphs of the theory. So they depend on a given attribution of scales. And you can see that they form a forest for the inclusion relation. That's the Zimmermann forest, if you like, or that's the Galavotti-Niccolo tree.
I'm sorry, what do you mean they form a forest?
For the inclusion relation, that is, if you draw the graph of the inclusion relation between them, you find a forest. If you draw the graph of the, no, not the graph of the inclusion relation, if you like, of the inclusion relation is partial ordering, and you draw the corresponding graph. This is a forest. But it means, well, it's not clear. Okay. So if you have a subgraph, it's said to be included in a graph if the lines there are there. So you have this structure. Okay. But you never have something which is like that. Because when you draw the story of the line attribution starting from the highest one, you will essentially always pick up by definition of what is a connected component, they will be disjoint, and then they will merge into larger and larger things. And that is the forest structure. And that's the Zimmermann or Galavotti-Niccolo or Kohn-Kreimer structure. That's exactly that. So you want more details about this?
Yeah, forest is misleading in this context.
Oh, you don't like, okay. Because if I draw, no, the question is if I draw lines like that to describe the inclusion relation, but not these lines, because when I know this is included in this and this in this, I don't need to. Then the object obtained is a forest. So abstractly to this drawing is associated this forest.
It's a nested sequence of subgraphs of a graph.
Right.
That's
Question?
what they call forest.
David, it's not clear.
We can say that sequence.
Another.
So it's just because the word forest is used with.
Okay, so what can, yes.
Combinatorial
Okay, so how would you like to call it?
No, but if you look at the given scale, at the scale I, which is not the lowest one, you really see a forest. You see all the upper scales and the scale I.
Okay, so this forest is abstract and has nothing to do with the forest which have been looked at until now, which were made of, well, yes, it's a forest for the inclusion relation between graphs.
An underlying forest.
Yes.
I think it's a nested set system.
Yes, but physicists call it a forest. Okay, Zimmermann called it a forest, and after that, everybody called it a forest. So, no, but there is an underlying forest. It's clear. Okay, so that's what I call the form a forest. But you can say they form a nested set of subgraphs on inclusion relation. Okay, so.
It's not possible that there is an element which is above these two ones?
No, here? No. Because if there is lines at this scale which connect this, because of the rule I gave for high subgraphs, these ones will be connected by these lines. So they will not be this. So it's impossible.
It's true that ultimately they become all connected. So it's more
not if you compute ultimately a connected function, yes. If you don't know. So it's more general to think that they might not. But interesting. No, but this is important. This is the key of renormalization. This is clearly, this structure is at the key of renormalization. This is the one which is important. Yes.
It's like
for everybody who studied renormalization, that's the key problem. Sorry?
It's like studying connected or not connected correlation function or taking.
Yeah, at the end, if you study a connected function, they will all merge into that, and the forest will be a tree called the Galavotti-Niccolo tree, if you like. But in fact, okay. And the Zimmermann forest is a subset of these where the nodes here are divergent, but I don't want to enter too early into this. I have to tell you about the two other ingredients now. Yes? You have a question? No, it's okay. So I have to tell you about what is the locality principle. It is completely independent of the dimension and of the model. It's simply the remark that every high subgraph sort of looks local when you look at it from the lowest scales. And the idea is that is very physical. Is to say the high subgraphs are connected by lines which are typically very short. So So they represent objects, if you like, the vertices are very closely packed in a high subgraph. And you observe it with lines which have very low frequencies so that do not distinguish the pixel inside. So it's like looking at a planet from far away. It looks like a point, okay? So that's completely independent of the dimension of the form of the planet and so on. So it's extremely general. So that is locality, and it only applies to the system of high subgraphs, because these are the only ones which look like that. So that's the locality principle. So suppose, for instance, inside a bigger subgraph, I draw perhaps just a part of the graph. Suppose you have these two lines which are very high in index scale, and these ones are very low, okay? Then the locality principle just tells you that from the point of view sort of these things, which are the only probes I have, for instance, to connect this to the outside world, well, this is like a point, essentially. That's just that.
So if you have a cycle, whatever cycle, and one of the indices is big and the others are small, one of them is...
Yeah, you have to have all the red indices to be all higher than all the blue. Then the blue guy cannot see very much whether this red thing is a point or not. That's all.
I wanted to say, if along a cycle, one is low and all the other one are high, it's like if the low one is not there, because you are probing with long distance, something which is short distance.
Yeah, you could, what you are telling me is as soon as you have a tree here which is high, these 2 points are close together. Well, but that's, yes, that's a good remark, but for reason I have to discuss later eventually with you, it's not what I am going to say here, okay? But what you say is the sounds correct. All right, so now you have power counting. So what is power counting? So power counting does depend on the dimension and on the kind of, for instance, of the fact that this is a 5-4 theory with degree 4 at the vertices, and if it's a 5-6, it's not the same thing. So the key question is the following one. The key question is, after spatial integration of the internal vertices of a high subgraph, save 1, then the question is, does the sum over the gap between the lowest internal and the highest external scale, that is between the red scale and the blue scale in the previous graph, does it converge or does it diverge? That's the key question. Well, if it converges, then the local effects represented by that subgraph are not terribly dangerous. But if it diverges, you have to do something. Well, after a bunch of massage, you see that because in the previous bound on my slice, because of this bound that was here, here, you remember the M2I factor for each line and this factor here, then you realize that these M2I's, you all collect them. So essentially, you get a factor M2I per line. And when you integrate a vertex, you get this because you integrate it with an exponential which decreases with a scaling factor M to the I. So how many?
The 4 is from dimension.
Yes. How many integrations should you do? Well, for a connected graph, you should do n-1 with these lines. And the last one is like kept for translation invariance. If you like, when you want to know what is the weight of this compared to an initial vertex like that, this had to be integrated anyway. So you should integrate only one of them sort of with respect to the center of mass of this drawing or so. And not all of them. All of them save 1. That's very important. OK, then you have to think about that. But when you are sure it's all of them save 1, you do this combination. In 4 dimensions, you find that it's only a function of the number of external position. And it's 4 minus n. And because when this number is negative, you have a sort of geometric series that you can sum over I. And if it's not negative, you cannot. So the question whether this, the answer to this question depends whether the subgraph has more or not than 4 external arguments. OK. For instance, the previous graph diverges logarithmically because you have 2 line factors, 2 red line factors, so 2m to the I, and 1 m-4i when you integrate that with respect to that. And again, you would need only a tree in some sense to do that. But let me forget about that for a moment. OK, so that's the mysterious sentence that physicists use when they say this is why 544 is perturbatively renormalizable. They say this because the only divergences that they found correspond to high subgraphs with n equals 2 and 4. And when they are inserted into ordinary larger graphs, because they look local from the point of view of the overrides, they look like a change in the initial coupling. Well, technically, they look like a change in the free couplings. The coupling constant for the case n equals 4, but the mass and wave function for the case n equals 2, because then there is a little bit more to find, which is a little bit analogous to when you probe a system, which is an electric system. You first see the charge, but after that, you see dipolar effects. And so in the case of the two-point function, because they are very divergent, you have to first extract the local effect and then a next effect, which is like a dipolar effect. But apart from that, these parameters appeared in the initial model. The only effects which diverge over the number of scales are related to change into these. So what we could say is that the parameters of the model do change with the observation scale, but not the structure of the model itself. It remains a 5/4 model. And this is what physicists call perturbative renormalizability. If you like, it's a kind of sophisticated self-similarity. The parameters change, but the theory remains a 5/4 theory. Okay, so that's what the people mean when they talk about that. So there is a problem now. We have to look at exactly how the parameters change to know the answer to the frustrating question of whether you are going to wander out of all these nice radius of convergence that were delivered in this room by cluster experts. Okay, so there seems to be what we call a Landau ghost, or kind of, because Landau was the first physicist to point very strongly at this phenomenon. He said, okay, essentially the main effect for the change of the coupling constant with scale has to do with this graph. Then you compute it, and you see that it amounts to say that at a lower scale, you have to add to the previous vertex this thing, which is this graph seen from that lower scale. But because you had to have this sign, okay, you rewrite this and you find this with a plus sign. It means that lambda grows with I. And in fact, this flow, it's well known that the quadratic flow diverges in a finite time. So this flow diverges. So you go out of any radius. So certainly you go out. And then that almost killed field theory, because in the 60s, the field theories that people were physically interested in had all this phenomenon. And I have then to show you a slide with which is entirely of physics. So okay, there was a surprising history that renormalization and field theory made a kind of comeback, because okay, I will go fast, but essentially some people found a new kind of theory called non-abelian gauge theory, based on a certain internal non-commutative, what this is called gauge group. And then other people succeeded to show they are renormalizable. Then still other people showed that they did not suffer from the Landau ghost. And they developed into a theory of nuclear forces. And then also around that time in the 70s, this guy, Wilson, enlarged the scope of this renormalization technique. And happy end, all the people in red in this case got the Nobel Prize. So it means that this was at the center, very much at the center of physics at that time, of physical preoccupation at that time. Okay. But nevertheless, although this is a happy story, it is not a very happy story from the point of view of mathematical physicists like me, because these theories, although without Landau ghost, they have conversely another problem, that the flow is still unbounded, but in the other direction when you go to very large scales. And this goes under the name of the confinement problem. And if you can solve it, there is a $1 million prize for that. But it's certainly very hard. So still frustrating. Yes.
This is not true.
Sorry?
Nobel did not get the Nobel Prize.
Good. That's a true combinatorics answer thing. All right. I will put a blue next time. Very, very good. Okay. So then I have to, unfortunately, go relatively fast into my subject of non-commutative field theory. So, well, non-commutative geometry is certainly now a rather big branch of mathematics, which replaces ordinary space with a space in which the multiplication of observables may not commute. So that looks a bit like what happens to phase space when you quantize a problem. And, but this could occur even in an ordinary space, perhaps, at a length that we have not yet probed experimentally. Well, it's a possibility. And I like to picture that like then space itself would become like a sort of non-commutative game. And the simplest of this game is called the Moyal space, R4 theta. So you would simply, for instance, the simplest, perhaps most naive thing you could do is you could say that between two coordinates, you might have a constant commutation relation with a certain scale, which might be perhaps very small. You know, before Planck, we didn't know about the Planck constant, so perhaps we don't know yet about this constant. I don't know. So if you look at this rule and continue it into, there is a unique way to continue it into an associative and non-commutative product called the Moyal-Weil star product. And you see that when you star product two functions at x, it is given by a combination of functions at different points. So it is a non-local. Okay, so you see that you can still see that the star multiplication of two plane waves is still a plane wave, but with a strange twist here.
And Vincent, go back for a second.
Yes.
So the ordinary symmetries of R4 are broken somehow.
Yes.
First and second coordinates get paired.
Yes, there is still a rotation invariance inside here, you see. So you have still an SO2 cross SO2. But this breaks Lorentz invariance. I'm going to break every possible imaginable rule. So I'm, I'm going to be very... yes, I'm going to add other rules, and I try to interest you into these new rules. Okay. So, well, after all, that's what lots of people gave us bad examples about. I mean, you told about the cohomology and cosmology and strings. No, not exactly strings. So I will follow in this footpath. But so quantum field theory on the Moyal space would be to try to extend the ordinary rules of field theory to that. And some motivations come from, well, lofty people who work on string theory or loop gravity and so on, because after all, quantizing gravity is a bit like quantizing space itself. But there are also, I would like to say that there are also more down-to-earth motivations. For instance, if you have a strong background field, it might be very interesting to express it with the non-commutative formalism. There is one quite obvious example, which is the quantum Hall effect. And but I think there are other examples of this kind, but that's really about physical applications. So I will not enter too much into it. So there are physical motivations. And when you look at what could be the 5-4 theory on Moyal space, R4 theta, the most naive thing you could do is to use the same action as before, and you could everywhere replace the products by a star product. But in fact, there is a property called traciality in the Moyal-Weil product, which tells you that as long as you have only two functions, the trace of it, that is the integral over the space, is the same with and without the star. And you can think about it by saying essentially this thing has cyclic group of permutation, but the cyclic group Z2 is the same as the permutation group Z2. And so there's no real difference between these things here and the previous one. But this one is completely new. So that's why I have to tell you about the new Moyal vertex. So this vertex, what is it in the former language? Well, if you look at it in the formal language, it can be computed explicitly because the rule of multiplication of plane waves was quadratic, so it can be computed. And you see that it is made of two parts. One part in X space is a non-local delta function, which is now a conservation of positions rather than a conservation of momentum. And then there is an oscillating factor here. So this rule tells you that x3 minus x4 is equal to x1 minus x2.
It is clear what is this integration in x's now, because this x's now there are some anti-commuting sums.
These things are now on R4 without the theta, if you like, and all the theta has been plugged there. So these are ordinary points on ordinary space. So this is ordinary integrals, but instead of having all the fields at the same point, so in ordinary space, I would have to replace all this thing by delta of x1 minus x2, delta of x1 minus x3, delta of x1 minus x4. It would pull all the things at the same point. But here it's more complicated, and the 4 fields at the vertex lie at the summit of a parallelogram. And there is an oscillation of this parallelogram, which is proportional to its area. That's the story of this vertex. That's it.
Is that you can do this theory only if you work instead of in 4 dimensions in an arbitrary dimension, this dimension must be even.
Yes, or you can put a degenerate theta matrix with one coordinates that commute with all others if you want to look at an odd dimensional theory. But clearly the theory seems to favor even dimensions.
And d equal 1 is easy, or d1?
No, d equals 1 is impossible.
No, d equal 2, sorry, I wanted to say.
D equals 2 is okay, it's like that.
So, but it's more solvable than d equal 4? Or
Oh, yes, much more. Just like 542 was much easier than 544. But our goal is really to go into 4 dimensions. But yes, 2 dimensions can be studied. It's easier.
So this propagator is horribly non-local.
Horribly. And the vertex is also horribly non-local. But wait a minute.
I mean, the magnitude doesn't change at all, no matter how big this parallelogram is.
Wait for the rest of the
Okay.
story. So, well, at the beginning, well, I think I'm going to lack of time, so, but I want to tell you the interesting aspects of the story. But, well, let me say one interesting aspect is, curiously, the amplitudes of planar graphs, let me not be, I will be more precise later of what that means, do not change. So there is a sector of the theory which doesn't feel the non-commutativity. Okay, so in particular, there was an infinite number of graphs which are planar and divergent in 544, so you cannot hope, as the initial founders of non-commutative field theory did, that non-commutativity of space-time kills the ultraviolet divergences. It's just wrong. There is still infinitely many divergent graphs in this case. Non-planar amplitudes also create a new type of divergence called infrared ultraviolet mixing, which is very surprising. It means that when you have non-planar graphs like this one, there is an additional oscillating factor compared to what was before the amplitude. So in the ordinary commutative theory, this diverges, but in the non-commutative field theory, that converges. But of course, when the external momenta p goes to 0, this oscillation disappears because this oscillation was what made this graph finite. In fact, you get a divergence when p goes to 0. Very surprising.
Sorry, what is this graph?
This graph is, well, you have now a cyclicity at the vertex, and the amplitude of this graph is not the same as the amplitude of this graph. So you have 2, should I say loops or self-loop or tadpole or whatever. Let's say loop. You have 2 loops. You have this loop, or you have 3 loops, in fact. The one which is up, the one which is down. These ones are planar and don't change. They have the same value as before. But this one becomes ultraviolet finite, but you pay it by an infrared singularity, which is very strong, because if you plug many of these into a line, you remember perhaps about renormals and so on, then you have a terrible infrared effect, which you can have as many of this power as you want. So you can make it diverge like a power 100 or 1000. So it looks very bad, and all correlations are affected, and the theory cannot be renormalized. Okay? So that was the situation around 2000. Okay, when this phenomenon, and for a while there was no way out of this problem. But then, in 2004, Grosse and Vulkenaar proposed a modification of the model. They said, okay, the model will look more symmetric, more beautiful, if we add to the covariance a term which is proportional to x squared. So it is a harmonic potential. Then, horrible, you break another thing. You break translation invariance, okay? Okay. But wait.
And where is x equals 0? In Paris?
So where is it?
Where is
yes, I depend. I think here they believe it's in Greenwich, but I think we do believe it's in Paris, of course. So this becomes then symmetric under a new kind of symmetry, because you see that here you have d mu's, and here you have x mu. So under the symmetry which exchanges p mu with x mu, this thing is now symmetric. And this is suggested by the fact that, curiously, when you exchange p and x in the vertex, it doesn't change. the vertex of an ordinary theory is very different in X space, where it is local, and in P space, where it is a global delta function. Here you had one delta and one oscillation. When you change, the delta becomes the oscillation, and the oscillation becomes the delta. So the vertex has this symmetry. So you could say, because the vertex has this symmetry, it's like in a gauge theory. The propagator should also have it. So they took the bold step to add this term. And then the theory becomes renormalizable at every order in lambda. And this result has now been proved through many methods. OK, I have not time to talk about the method. But what I am trying to tell you now is in which way the ingredients of the renormalization recipe will change in this story. So let's go on. So there is a new propagator, of course, and it can be computed because p squared plus x squared, the kernel of it in parametric space is called by mathematicians the Muller kernel. And you can essentially do it. And the reason is there is a difficulty because p and x don't commute. But in some sense, you take a limit of a Trotter formula, and it's still quadratic, and you can compute it. But now it's the functions are hyperbolic. You see, previously I had alphas in the heat kernel, but this is a Muller kernel, and therefore I have sinh. But still, I can do it, and I see that when alpha is small, the heat kernel is there, sort of hidden there. You see, when alpha is small, you still find the decrease here in x minus y squared divided by alpha, and then you find again the analog of 1 over alpha squared. But this is essentially due to the breaking of translation invariance. But when alpha equals 0, this becomes weaker and weaker. So you sort of recover translation invariance asymptotically in the ultraviolet. So it's complicated, but let's admit it. So now, yes, you have a question.
You said that in the symmetry you are exchanging 2 times here and 2 times here. So I would have guessed that in order to tune the things, omega and theta were related.
Yes, in fact, the model is covariant under the symmetry, under the Langman-Szabo symmetry at omega different from 1, and it's exactly invariant at omega equals 1, and omega equals 1 will play a big role in what follows.
Just 1, not theta square.
No. Well, because I absorb the theta into the x tilde. I absorb the theta into the x tilde, so that's why it's omega equals 1. Sorry. OK. So, well, now the non-commutative renormalization relies still on the combination of 3 elements, but everything is new. You have a new scale decomposition, a new locality principle, and a new power counting. So, as in the commutative case, the first 2 are quite universal, but the third depends on the details of the model. So, the scale decomposition is still the same idea. You take the Muller formula and you cut. And then you get this. You get that at the high scale I, you still have this, which is exactly as before, but you have a new effect, which is this. So you have a very weak kind of decay of x with respect, or y with respect to the preferred position of Paris. Okay. So then you have this. This is a new scale. At high energy, you are allowed to go out of Paris, but if you are low energy, you are sticked. Okay? You are stuck to remain near Paris, which after all is a good thing. So, well, depends on the point. So the corresponding new renormalization group is a kind of mixture of what was previously the ultraviolet and infrared notions. You cannot say really that it is only short distance. It would miss something to say it, but still it's a bit like that. And, okay, what is similar to the case before where I had the mass is that there is only really a half direction for this renormalization group. So I'm sorry, I have to speed up a little bit. So here I have to, but I have to tell you about this. So what is surprising is that there is still a new locality principle here. That is, I was surprised to understand that when you look at a graph which is at a high subgraph in this language, it still look exactly like a Moyal product from the point of view of the low legs. So but it requires something new. So you have this new locality rule only for high subgraphs of a certain particular type. The particular type is that they have to be planar, and all the external lines must arrive on the same external phase. So I will explain this a little bit more. But look at, for instance, this graph is of this type. Now you will immediately understand what I call the moiality, is that if I take, remember these were the high energy line. Suppose you take this red energy, the red scale much higher than the blue scale. It means that you will contract these 2 points together. So what will happen is the following. These 2 points will, you pull on these 2 points, they contract together. You look at it from these points there. You see that because these coincide, this is parallel to this, which is parallel to this, and therefore this is now a parallelogram too. And now you see that the area of this parallelogram is, of course, the sum of the two red ones, of the two green ones. And if the thing was not planar, then it would be twisted and they would not add the correct way. So you understand that there is a locality principle, but it does not apply to every graph. It applies to the high subgraphs, which are planar with a single external phase. But what is nice is that when you do the power counting, that's exactly what you will need. Because there is also a new power counting, and okay, the graphs are really ribbon graphs, and it depends on whether it is on the genus of the graph and the number of external faces, so these invariants. Okay, so this probably you know very well, so I can go fast. So when you have a planar graph, so I think you call it a map, perhaps. Or, okay, then if you have a map, you have a number of vertices, of lines, of external faces, etc., and you have a layers relation. And now the new power counting involves this, so that only the graphs, so this E, I am sorry, this is again a misprint, this E should be an N. It is the number of external lines of before that I called N before, so this E is like N. And you see that you have the same factor as before, but improved when the genus is bigger than 0 or when the number of external faces is bigger than 1. So these improvements precisely tell you that you have to renormalize only when these two numbers are 0. But that's the case that you can renormalize by the moiality process. And that's why the theory is renormalizable. Okay, so I will not have time to show you graphs because, well, it's how you compute the genus and so on, but I think I have to go. So power counting tells us that only the planar graphs with 2 and 4 external legs need renormalization, and moiality principle tells you that they can be renormalized, and therefore you have again a renormalization principle that tells you that the structure of the theory is conserved under change of scale, but the coefficients vary. And now we can return to our big frustration. Remember, our big frustration was that the flow was going out of the domain of analyticity. So we are now ready to enter into ghost hunting mode, and we find there is no Landau ghost in this 5-star for theory. So this was found at first order by Grosse and Vulkenaar, and then we extended it to any order. And I have, okay.
And what happens?
Well, what happened is, well,
no, I mean,
no,
the answer is that
something happened like that, but let me say another way.
Does the lambda not, I mean, the ghost was the lambda grows as you iterate.
This is the answer to the question, probably. So there is a double flow now of both the lambda and the omega parameter. Something very nice happened, which is that the omega goes to 1, which is a very special point where the symmetry becomes exact, and that stops the growth of the Landau ghost. So the ordinary Landau ghost was going like that, and now it is going to be tamed.
This is like Kahan-Szymanczyk equation? Or
yes,
what?
in the Kahan-Szymanczyk equation, you have now two parameters, and you find automatically a fixed point, no matter from how small. If you start from small lambda, you will remain at a little bit bigger lambda, but not very large. And you can remain inside the Borel radius of the
So it makes sense.
Yes, sorry?
It makes sense starting from finite lambda and 0 omega, which is the physical one in which you do not have.
Yes, so if you try to connect to the physical problem, yes. But suppose this would be a modification of the world at high energy. Then you don't need to solve the Landau ghost for the initial problem because the world would be non-commutative at high energy. You need only to connect to the asymptotically free 544 in the infrared, which would be perfectly okay.
Here it looks like that
well,
there's
There's not
just
one fixed point,
just
but
a weird conjecture, of course.
it looks like there's not one fixed point, but a line of fixed points.
Well,
omega equals 1 and lambda equals anything.
Yes, exactly. There's a line of fixed point. You automatically go into
You'll
that.
hit one point.
Yes, you will
depending on the
automatically.
initial condition.
It's a kind of automatic self-stabilizing thing. Okay, so, all right. So now the last few, well, do I have 2 minutes? Or? 2 minutes, okay. So in 2 minutes, I have to tell you the next stage of the story, which is the constructive aspect of this. So for the constructive aspect, this is very tantalizing because for the first time I find a kind of a theory rather simple that has no Landau-Gauss. So I would like to transform it into a constructive theory. But then I have a problem, which is that it cannot be treated through the ordinary cluster expansion because essentially the interaction is non-local. So one has to do something different. So, well, there is a new expansion called the loop vertices expansion, which solves this problem and which is based on cacti. Okay, so, and in a bonus, it applies to ordinary field theory, and it allows to do the single state cluster expansion, for instance, of the 5-4 theory that Malek showed us, in, without any cubes and so on. And we call it the constructive theory without tears, but you will hear more by Jacques Magnin about that. So in just 1 minute now, let me say that we can map the Grosso-Vulkenaar model into a kind of complicated matrix model. And for a matrix model, for a simplified matrix model with a large number of components, with this is the usual grand Gaussian ensemble unitary measure, then we apply the method of intermediate field. That is, we can transform this quartic interaction into a trilinear one with an intermediate field by completing a square. And then we can find a formula for the normalization, which involves here a kind of tensor operator where this intermediate field acts on one side of the ribbon propagators. But the big thing is that this operator is self-adjoint. So with an I in front, it is anti-Hermitian. So then what we do is, yes.
Stars were Moyal.
Sorry?
Stars is like Moyal.
Yes. No. Here, sorry. This, yeah. Okay. This is a model with a complex field. Sorry. And this star should be a bar.
It's a star of complex non-unity.
Yes. I must say I have not reread this, and I should have put a bar. No. This is an ordinary matrix product. Okay. But then. Okay, so you write the vertex like that, minus trace log, and you expand the exponential, and you apply the Forest formula, exactly the one that Malek explained. And then what do you get is a formula for the log of the partition function. But then there is for instance, you get this theorem that the previous series is absolutely convergent for lambda small enough, and it is Borel summable uniformly in n when n gets large. So it's very easy to prove the theorem without this expansion if you don't search for these three things. But if you add this, it becomes much harder. And that's what the previous expansion solves. And essentially, this is because there is a certain composition of operator bounds. And Jacques Magnin is going to tell you more about this, so I just pass. So essentially, the result is expressed as a kind of cactus in which you have ribbon propagators, and here you have the tree. And here are resummed all the intermediate fields, you see. But when they contract from there to there, they have a weakening parameter, which is the one that of the Bridges-Kennedy formula. Okay, so they are all hidden there, and all the other vertices are sort of hidden there. But now what is quite amazing is that because here you have a 1/1 plus I times an operator, which is Hermitian, you don't need to know what the operator is, but its norm is bounded by 1. Because 1/1 plus I times an Hermitian is bounded by 1. So when you do the product of all these operators there, following the path around the tree, you get an enormous product of operators bounded in norm by 1, and the trace of this is bounded by n, and you save an enormous number of powers of n in your estimate. So that's how you can essentially treat it. But my conclusion is that to complete the construction of this model, you need to write the multiscale version of that argument, and that's essentially in progress.
So, are there other questions?
I have one.
Yes.
So, it looked to me like
Yes.
you put,
Mm.
well, a magnetic field usually makes the P's non-commute in a strange way, and it looks like you've done something like putting a magnetic field in momentum space. In what sense is
Yes.
is that what this
Yeah.
model is?
The Gross-Wilkenaar modification of the propagator is not exactly like putting a constant magnetic field, because then you would have an additional term. But okay, so it's in a way it's simpler, but what you say is perhaps physically more interesting in some sense. So if you were to consider the propagator with a covariant derivative in a constant magnetic field, in addition to this, you would have a term which is in P wedge product with X. And this P wedge product with X will still have the Langman-Szabo symmetry. So, and you could have a third parameter, and the magnetic field is then when these two coefficients are equal. This case is like you put only half of the effect of the magnetic field. So you cheat a little bit. But the problem is when you put the B also, it becomes more singular. And then, okay, it's even richer. But I think it's a bit like going to a critical model. But this is essentially, okay, the easy part of the story. And then I think that you need that, for instance, for the quantum for applications to the quantum Mole effect. Then you would be in 2 dimensions, and you would put the term I am talking about. But that's another story.
Well, the other question, I guess,
Yep.
is it possible that you could find other kinds of vertices that besides the Moyal vertex, which would also have these nice properties?
Okay, so if you take phi 6 or so, it will not be renormalizable in 4, just like it was before, so because of this power counting problem. But for instance, phi 6 is renormalizable in 3 dimensions when only two commutes and one is only 2 anti-commute and 1 commute. So you have a certain parallel with field theory. But to answer also your question, I should say we can also try to look at this model on a more complicated background. For instance, a curved background. That's also something in progress.
You don't, I mean, you think this is essentially unique, this way of arranging them at a parallelogram. There's not any other kind of geometry.
Well, it's because we are looking at a kind of, well, of course, it's a very vague argument, but the idea is if you have a very complicated commutation relation and you expand it into powers of x, at small x, the first thing you might see is an anti-commutator. So it's like a kind of tangent space. So doing this ultraviolet analysis is this kind of tangent space is going to automatically lead you to this kind of vertex, essentially.
I was
Yes.
thinking that, for example, tetrahedron, if you
Yes.
force them to collapse on 2 vertices, goes into tetrahedron.
Yes.
So this would be one of the examples.
No, that's another extension. That has to do with loop gravity or things like that. It will have to do with gravity. This model doesn't really contain gravity. So gluing tetrahedron and so on is a kind of extension, clearly, of this model. But I think it's quite curious that in this model is a matrix model, you see. And it's quite curious that the matrix model sort of regularized in a quite natural way the Landau goes. For me, that was a big surprise. Was not expected, I think, by anybody. Well, the people who founded non-commutative field theory hoped that it would be better behaved in the ultraviolet limit. But the reason for which they are finally true is very sophisticated, in fact. So we have to probe it deeper. We have to understand why there is this fixed point in a more, well, in a better way, because there's a kind of non-trivial fixed point like the conformal symmetry of 2 dimensions creates non-trivial models, you know. So I think we have to work on it more. But that's also fun.
It's gravity without extra mass.
If,
Just gravity.
no, it's like 2-dimensional gravity, essentially, not like 3 or 4-dimensional gravity. In 2-dimensional gravity, you have ribbons and you have just Riemann surfaces. But it's a kind of Euclidean one, so that's why I asked about Lorentzian one. It's a kind of Euclidean 2D gravity, yes.
What happens to symmetries? They will
Well, they have been broken and we have to recover them. There are other people who have done that before, the people who work with supersymmetry, and they have a lot of trouble finding back the ordinary world. So I suppose we will be, unfortunately, in front of the same problem. It's not easy to go back when you have done all these bad things.
Lorentzian gravity is maybe universal, otherwise you get the Euclidean gravity.
Yes, so that's a question that I would like to.
John?
Yes.
So is there some sense in which, in some momentum range, the symmetry is approximate, or some limit where this goes over to normal theory?
Okay, so then after that, there is a question of once you have a control of the mathematics of the model, you want to understand better how to connect it to physical application. So there are different. If you look at a problem like Hall effect, it will be completely different from a problem like, for instance, if you imagine this could be useful for physics beyond the standard model. For physics beyond the standard model, you would say this is really the region with omega equals 1 would be far in the ultraviolet, and you would like to connect to omega equals 0. That is the normal world where there is no favored point at longer distance. And you would like also to sort of erase the effect of theta. So this is quite singular limit. We have been introducing another model which is related to this one, but a bit different, to try to understand the kind of intermediate situation. Because although in this case the ultraviolet model is good because you have tamed the Landau ghost, the infrared, when you want to force omega to come to 0, you would find back this problem. So you have to very fine-tune the things if you want to go to an infrared model. So there is another model which we have introduced recently, which is supposed to go a bit in this direction.
So I thought the omega goes to 1 by the renormalization group law. So what do you mean by force omega?
Okay, where was it? This picture with the omega equals 1 that Alan asked me to show. It was somewhere there. Yes. So this picture. What was exactly your question?
I thought the omega goes to 1 in the infrared anyway because of this flow.
Well, if you interpret this as, here you have this duality. So infrared and ultraviolet are mixed. So there is a problem of what do you interpret as the old infrared and the old ultraviolet. So if you interpret the way I did, namely alpha going to 0 as the kind of the ultraviolet limit, then you have omega equals 1 in the ultraviolet. And then you go down to omega eventually going to 0. If you tune correctly your trajectory, probably you can go to a kind of critical point where omega goes to 0 in the infrared, and that's what you would like to see because you don't see any harmonic potential in the ordinary world. But then you have to see whether this is compatible with physics, or if this phenomenon goes fast enough, or if you need to accelerate it or so. You have to look at scales then, if you want to do physics beyond the standard.
So you said that the I only takes values in n, basically. It's 1/2 of
yes,
the
yes. Yes. And you have to tune it very, yes. If you do normally your flow, here you arrive in the matrix base at the matrix index equals 0, and then you cannot go further down. But you have to glue it in a more subtle way to an infrared limit to see the infrared space sort of reappearing.
You expect that maybe you could glue it to the ordinary?
Yeah, we hope so. But this is a subtle point, and we are working on it. But for the moment, right like it is more like just half of the story. Okay.
Are we sure that there is no canonical transformation which proves somehow with some, I don't know, integration by paths, things like that, that putting the origin here or there is actually the same action?
Yes, you mean you could also interpret this position of the particular point as a breaking of as a selection of a particular vacuum, and you will. No, is it your?
So maybe if it were flat around the vacuum, you are just expanding here or there.
Yes.
For example, expanding the basis of the harmonic oscillator, a translational invariant.
No, this is really translation, breaking translation invariance. This term. It's not just, yes, if you were doing what David said, namely put a constant magnetic field, and if the coefficients of the x squared term is equal to the coefficient of x wedge p, then you recover magnetic translations. That is, the situation is such that the gauge connection that you choose is not translation invariance, but the field was. So the final theory and the observables are. But here, it's a case where really you broke translation. I have to admit, you really broke translation invariance. So you have a hard time to recover it eventually later.
I think we ought to have the rest of the conversation later. I do have one announcement, which is the group photo will be taken at 12:30 tomorrow after the last talk. You'll lead us to the.
Actually, it's Sarah from who was the librarian.
So thank you very much, Vincent.